Let's talk about the simple pendulum. So simple pendulum, pendulum basically we have all the mass is a point mass. In other words, we're not worrying about the size of this. So I have a point mass here. I have a string of, or something holding up of length L. This is massless. Traditionally, when you're dealing with pendulums, you care about that angle right there. So the angle from the vertical instead of from the horizontal. And so the big question here is, does it obey Hooke's law, or is this simple harmonic motion as this thing oscillates back and forth? Well, let's work it out. So we do a force diagram here of the mass. I have tension acting this way. I have weight acting down. There is no friction. And of course, no air resistance. Now, the direction of acceleration is going to accelerate in that direction. It's going to accelerate that way. So tension is perpendicular to that. Let's set up my coordinate axis here, I and j. So I'm going to break weight up into its components. I have a certain amount of weight that way and a certain amount of weight this way. I know that this angle right here is theta, because two parallel lines cut by transverse corresponding angles are congruent. So if I break weight up here, I have weight acting down. I'm breaking it up into components where this angle here is theta. So this is W sine theta, and this is W cosine theta. So I have tension acting this way. I have W cosine theta acting that way, and W sine theta acting that way. We now have, we do our equations of motion now. So I know that tension minus W cosine theta is not equal to 0. It's equal to mass times v squared over r. It is centripetal acceleration. It is changing directions. I also know that it is changing speed as well. So I have W sine theta is equal to mass times acceleration. Now I do need to be careful here. I have acceleration being positive, so I, j, k is coming out at us. This angle here is that way. In other words, if theta is equal to 0 here, this is where theta is equal to 0. This has been displaced in that direction, in the clockwise direction, and so I've moved it in the clockwise direction. So the direction of this angle is actually down. So this is the sign of negative theta, because direction does matter here. Is equal to mass times acceleration. So mg, negative mg sine theta is equal to mass times acceleration. Now we've got an issue here. I have this is an angular quantity, that is a linear quantity, and we need to correspond them. Well, let's go back to v equals omega r. Well, if I take the change in speed, therefore is omega, change in omega times r. If I divide by the amount of time that is happening here, then I have acceleration is equal to angular acceleration times r. And so this becomes negative mg sine theta is equal to m alpha times r, which is L here. So if we take that equation there, so I have negative mg sine theta equals m alpha L. That's equal to negative g sine theta is equal to L alpha. We still have an issue here in the fact that this angle right here is trapped inside the sine function. So now we employ what is known as the small angle approximation. Which I will sometimes abbreviate as SAA. So the small angle approximation says that if theta is small, so we're dealing with radians here, so that's why there's no units written there. So if theta is much less than 1, then sine of theta is approximately equal to theta, which is approximately equal to tangent of theta. How accurate is this? So let's flash in. I think I got this from Wikipedia. So we have the three functions here. I wrote x instead of theta here, but we have x in red, sine theta in green, and tangent of theta in blue here. So as the angle gets bigger, notice that when the angle is small, they hang out relatively close together, but then they start to spread apart. But as long as the angle is small, these three things are all basically overlapping each other. And so that is what we're talking about there. So if the angle is small, so in other words, I take my pendulum, I move it out a little bit, and then I let go and let it oscillate back and forth. I don't pull it all the way out to 90 degrees to do it. And so therefore, this now becomes negative g theta equals L alpha, given that assumption. And this is the right format because we had negative kx is equal to ma. We now have a Hooke's law approximate here. I know that omega was equal to the square root of k over m. Well, for this one, instead of k over m, it's now g over L. I know the period is equal to 2 pi over omega, which is 2 pi times the square root of m over k. For something in true simple harmonic motion, well, this now becomes the period for a simple pendulum is 2 pi times the square root of L over g. Recognize the power of this. With this, we now have a way of timing. Before there was accurate clocks, we do have something like this. And so someone like Galileo is able to start actually doing relatively accurate timing. Matter of fact, we can figure out what 1 second is. How long does it need to be to make 1 second? So I want my period to be 1 second. So that's equal to 2 pi times the square root of L over 9.8. At this point, I have the square root of L over 9.8 is equal to 0.1591549, so on. I square both sides. So I have L over 9.8 equals 0.02533, and so on. Multiply times 9.8. And so the length of the pendulum, where almost all the mass is hanging down at the bottom, is 0.248 meters, which is approximately 25 centimeters. Now this allows us to do more than just time to the nearest second. This actually allows us to time to a quarter of a second. Because if I pull the pendulum back not too far, it takes 1 second to go there and back, which means it takes a half second to get to here, and it takes a quarter second to get to here. So this would be a quarter of a second. That would be another quarter of a second. That would be another quarter of a second. And that would be another quarter of a second. And so this gives us incredible power, especially early on, to be able to start doing somewhat accurate timing, down to at least a quarter of a second. Now, at some point, it becomes a lot more difficult, and there become error bars. That's a whole mess there, but at least this gets us on the right step before we have precision timing.